In this challenge, the team looked to develop an opportunity for PhiSat2 class microsats, testing how onboard ML can be used to reduce data transmission needs by enabling autonomous data selection of extreme events, or hotspots. Novelty detection is certainly a compelling problem for onboard ML. It has the potential to increase the value of downlinked data, and it is the premise for many use cases, such as disaster response, biology monitoring, or even continual learning, to cite a few. We at Google Cloud are very excited about the potential of machine learning payloads, and this application is an eye-opener to what's possible. I'd like to introduce you the Extreme Event Hotspots using ML on Board challenge.
Thanks very much, and hi, everyone. We are the ML payload team. This is us, the researchers. So Vit, Anna, Danielle, and myself, James. Our mentors, Valentina, Gonzalo, and Valentina, and our advisors, Brad and Chris. I want to give a bit of the motivation for our project. So satellites are orbiting and continuously observing the Earth's surface, but they beam down images they capture without actually considering what is in those images. They don't know whether what they're looking at is something interesting or important. The scene might not have changed since the last time it was observed, and they beam it down even though there's no new information in that. And downlinking the images comes with a cost, as we need to build more or higher capacity ground stations to receive those extra images. They also can't prioritize to get the interesting images down faster. So an intelligent satellite, which can interpret images, can boost data efficiency and decrease latency for those most pertinent images. But what makes a satellite image interesting? Well, for rapid events like fires, landslides, and floods, the satellite imagery can be used by first responders. Here, latency really matters. But there are many events we're interested in, and they come in all sorts of forms. They could be hurricane damage or oil spills, volcanic activity, deforestation, shifting drought conditions, all sorts. And these are all changes. That's what we're actually interested in from the satellite observations, is change. And if we can build a machine learning model which can recognize change, then a satellite could recognize all of these hotspots and more as being important. Currently, the machine learning models which run on board are supervised and only trained to spot one of these types. For example, the FDL 2019 project, World Floods, looks for floods. But in order to give the satellite more flexibility, more autonomy, we want something more generalized, something unsupervised, so it can capture all sorts of change. And that's what we've been building.
So let's have a look at one of those changes. These are two images, one before and one after an event. Here we can see the first change that is very clear. It is a flood event. It is in the middle of the screen. The river changes shape, changes color, becomes thicker. It's very visible. But there is another change. For example, there is snow which fell on the mountains. And this is another change which is very interesting because, as well as the flood before, it adds information, meaningful information to the representation that we have of the scene. Yet, if we look at the same image now on a video, we can see that those are not the only changes in this environment. We can see, yes, the flood, the snow, but there are also a lot of minimum, very small nuances, very small changes that are made, for example, by the noise on the satellite sensor or lighting condition, atmospheric condition, and even clouds that do not bring much more information to the knowledge that we have of the environment. So we're not interested in those.
Thank you, Danielle. So let's look at the fundamental question which is behind the problem, behind this challenge. And that is to answer how to compare two images to detect relevant change. So not to be kind of firing on the changes that Daniel was describing, so the small sort of just fluctuation between maybe sensory noise or maybe some small changes within the scene, natural changes, but how to trigger on something that is kind of substantial. Well, one way would be comparing between the kind of just the pixel space. So basically just between the pixels, and that would be kind of problematic because that would be sensitive to this kind of noise. In order to kind of fix that, we have been training a unsupervised variational autoencoder model, which is a machine learning model, which is tasked to take images from the sort of input side, encode them in this much smaller representation space that we call like bottleneck, and then using only information inside this bottleneck, again, reconstruct it on the sort of output side. And so by doing this, we are forcing this model to kind of throw away all the redundant information and maybe focus only on the important things which could describe the data. So it kind of learns how to understand this data. And how would we use this model to kind of maybe make some comparisons with change? Well, so instead of looking at the pixel values and comparing there, we could look at these encoded feature vectors, so these bottlenecks, and kind of look at the differences and distances in this latent space. And so what we hope and what we can see actually is that comparisons inside this latent space are more robust to this kind of noise. And yeah, right, let's see how this would be even used on a real world satellite. Well, we kind of hope that using this decision-making mechanism on board, we could make some intelligent choices already there. And so if a satellite seeing a new image of the same scene that it kind of saw before, if it is able to decide that there is something which has changed significantly, then it can decide to prioritize downlink of this information. And that could be perhaps alerting someone or just updating some information on this new content. If there is no relevant change, maybe it can still downlink it if there is enough bandwidth, but that is always limited. More or less, I mean, in addition, we actually also can make kind of more comparisons, not only with the previous state and the new state, but also with a whole memory of images. So as many images in the past as we can kind of save in theory. And using this latent representation, the advantage is that we have roughly 100 times smaller dimensionality of these vectors. So it is also much more easier to save many more images from that in this representation. And right now, let's look at how these models can actually do on some real world data.
Thank you, Vit. So these are the results of our model identifying an area of change, in this case occurring as a result of flooding. So on the left here, there are images from before and after the flood, and also a binary mask showing in yellow where the change has occurred. And we can actually see that quite obviously in this image where the river has turned brown as a result of the flooding. On the right are the results of our model, both for the VAE that Vit just described, and also a baseline constructed by taking the difference between images in pixel space. And we can see from this that both methods identify the regions of change. And more than that, the machine learning method using the VAE also gives much less noisy predictions. These are some examples of change detection using the VAE model for other types of change. Specifically here, we have fires, hurricanes, and landslides. So from left to right, this image shows examples of images before the event, examples after the event, where you can see what changes have occurred, for example, the burn scar from the fire, a change mask showing ground truth of the change, and finally, the predictions of our model. In all these cases, our VAE model is correctly identifying the regions of interesting changes. Finally, this table shows a summary of quantitative results using area under the precision recall curve as a metric, where higher numbers here are better. So here we compare the two autoencoder models, VAE and VAE100, to a cosine baseline in pixel space and also a random baseline corresponding to downlinking everything without any intelligent information extraction. For hurricanes, wildfires, and floods, the VAEs outperform the baselines, while for landslides, performance of the VAEs is roughly equivalent to the baselines, but with the added advantage that we're storing much smaller images due to that latent space compression. These results demonstrate that our unsupervised model can indeed detect interesting changes.
So let's summarize our achievements. First of all, we developed an unsupervised change detection pipeline that we called Raven using a variation autoencoder model, and we demonstrated that this can be used to detect new types of extreme events. In doing so, we also built a library and tools and a dataset that we aim to release to the community to foster the research in this field. And we can also see on the left panel that we actually run one of those models in the board that Chris is showing in the picture, which emulates the hardware that you can find on a real satellite. We'd like to leave you with this image. So you may have heard in the headlines what happens in Greece, where there are wildfires raging in, for example, here near Athens, the capital. And you can see from the image on the left, which is the image before, and the image in the center, which is the image after, that there is a huge burnt area. And on the rightmost image is our model predicting that change. We can clearly see the burnt area firing up in the top right, but there is also a small area on the bottom left, which is highlighted, which is not seen by hand, but it is actually a burnt area. This is the end of our presentation. We'd like to thank our advisors and mentors for the help and the whole FDL community and all our partners because they made it happen.
Wonderful, wonderful stuff, Payloads team. And also I wanted to congratulate you for the different modes of work from software to hardware to labeling. You've really done some phenomenal stuff. So if we could invite our panel to jump on and turn your cameras on and microphones. It'd be nice to hear some thoughts and reflections on this work. And I can see Alison jumping in, and Massey, and hopefully Simon and Chetty. Excellent. Thanks so much for joining. So perhaps the first question, and Kelsey, welcome. Hope the coffee's kicking in. And really nice to see you. Thanks for joining. So really, question to the panel: why does this work matter? What should the takeaway be for the audience?
I can jump in if that's okay. So I think for me, I have kind of a personal connection for two reasons. The first being my job as a satellite operator. I operate the satellites at Planet in our Dove constellation. So anything that makes our satellites quote unquote smarter and gives them this sort of intelligence to make decisions as to what pictures are or are not important is just an incredible breakthrough. I mean, ground station resources are limited. Satellites can only communicate with the ground station when they can pass over that area of Earth. And so if we can have our satellites make these decisions as to what pictures contain information that's relevant, that would just be, groundbreaking, especially from a satellite operator perspective. Limiting any sort of human interaction just makes it better, especially for major constellations. And from a other personal perspective, I mean, I live in California, and wildfires, I've never experienced wildfires before until I moved to California, and the idea that we can use this sort of technology to reduce the latency and support first responders and in determining, where the fires are moving and any sort of reduction in latency between identifying these sort of natural disasters, I think will be really life-saving ultimately.
Thanks, Kelsey. Massey, I saw you're nodding, and I don't know, why is this exciting from a machine learning perspective?
So I would say two things. The first one is that this is really kind of within a trend that is going on in AI, across areas, right? So you see actually kind of our phones and our consumer devices becoming more and more smart, and actually these AIs being applied there. And there are a lot of advantages of in terms of latency, in terms of privacy, in terms of communication needs of those devices. So, it's time that we start moving this kind of intelligence also on our satellites. And if you look at it from a wider perspective, in a sense, we have done tremendous progress in the last 4 decades in terms of putting sensors in the sky. You can actually think about having our eyes in the sky now, collecting a huge amount of information. But our brains that parse all that information are always on Earth. And there is a bottleneck there. And I think actually the team had really hit the kind of crucial spot about enabling this kind of intelligence to also go up in the sky, live where the sensors are, and then be smart about what they communicate to all the rest of us. To Kelsey's point, I also live in California, and wildfire is a big problem here. But as the team kind of mentioned, it's flooding. It's just in general change that you want to know about. But change on Earth is all the time, and you want to know what is the change that really matters. And for that, you need a brain in the sky. So congratulations to the team. This is really impactful.
Chaddy and Alison, same question to you. What, from a machine learning perspective, this is unsupervised learning again. What's the difference between where we have been for the last, if you like, 5 years of machine learning and what's happening now in unsupervised work?
Chaddy, you can take that.
Go for it, Alison, if you prefer, but as you wish.
There is just a constantly evolving, fast pace, improvement over improvement over improvement. The various techniques that are coming into play with, generative imagery and creating and coupling with synthetic data, for example. There's so much actually happening. But from my point of view, intelligence in orbit, let's call them smart satellites. It will allow us, the autonomy of a satellite and huge constellations of satellites in a growing mesh right around the globe actually allows us to monitor all kinds of these very scary situations. And it's not just the obvious. ESA, Esrin, Pierre-Philippe et al. They put out this fantastic publication a couple of years ago on 99 different use cases. James mentioned a few of them, but one of the not so obvious is determining grassland v forest. Because our most crucial and time constrained problem now is acting on all of these cascading catastrophic problems, that we hear about. We know that forests, for example, help cool, but so far as permafrost, they actually warm and accelerate thawing. So there's a very, very urgent need to switch these massive areas, like Siberia to tundra, to grasslands. And we can easily do this with smart satellite constellations, with the mesh growing denser and denser as we put more satellites into orbit. And we can actually do the work, not just talk about it. And the embeddings work as well will actually speed things up, from the labeling point of view. But I think pulling in and coupling synthetic data along with real world, just like we do in the self-driving car scenarios, for example, it's a brave new world. And whether it's, Jetson or traditional FPGA that you're actually putting up into orbit, I'll stand by this statement to anyone. Waiting a few more years for for extensive testing for perfection is literally wasting precious time. And we have COTS, or commercial off-the-shelf hardware, on Mars right now. Qualcomm's Snapdragon and Ingenuity. It's actually operating on Mars, right now. So we need to act very, very quickly. And this work and the embedding work is really, really going to push actual action, which is what we need to do now, like by the end of the year, or early next year, not just talking about it. So congrats to all the teams. It's fantastic work.
I don't know what I can add over here, but just maybe a few sentences. But for me, this project is more about one step towards getting, some kind of fully autonomous, in fact, observation satellites. And this is important to say. And the important thing for me as a researcher in machine learning was to see that you guys, you worked on really interesting problems in terms of, using a variational autoencoder, so adding a little bit of Bayesian log over here, and, be able, in fact, to work on this idea of doing unsupervised learning or semi-supervised learning. These are really hot topics right now. because as you can imagine, we probably won't be able to label all the images that we get on different bands, on different, you know, positions and so on and so forth. So this is really a good approach, you know, towards what we really, you know, can dream of. And yeah, I mean, this was really a great work. Congrats.
Thank you. Simon, you're in the business of making intelligent, smart satellite constellations, those sort of things, and that Alison was talking about. You're actually doing it at D-Orbit. I was wondering if you wanted to have the closing word just to reflect on what you've seen.
Well, thank you, James. Yes, as you say, we're in the mode of helping to develop, to build these constellations with our sort of launch service. We've had 3 missions in the last 9 months. The last one, of course, we're really happy to have the FDL 2019 Royal Floods application on board, which we're really looking forward to demonstrating the results of that in the next few weeks. And this work done this year, I think, is a sort of fundamental, foundational capability that could be applied to all of the use cases and the benefits that we've been talked about so far, really enabling a capability which allows others to exploit all of these new technologies and the availability of new hardware in space, and kind of unlocking like an inherent value that's already there in many of the spacecraft that's already in orbit and will be launched in the next few years. So I think it's sort of the real-time responses to space data is starting another step in the evolution of how Earth observation is used for real daily use, which can benefit, you know, mankind in many ways.
Thank you, Simon. So again, I sense there's like a lot of conversational branch possibilities here, and we're lucky that our colleagues at ESA are here to sort of reflect on this. So I wanted to just prepare them to get their cameras on, and hopefully, Chris, you can join me and just having a little reflection with ESA. But I wanted to thank the panel. We're going to play a little film just for 20 seconds, and we'll be right back to talk to our friends from FELAB and ESOC.